Okay, geometry students, appreciate you finding time to get your notes taken care of. Today we have the final set of notes for the fall semester, and it's also the final set of notes for Unit 4, and that is on special segments in triangles. Please copy down your title and the date. These notes are for December the 11th, and also your objectives. Your stated objective is to acquire new vocabulary and properties for special segments in triangles. On your assignment, student will demonstrate the ability to, apply new rules surrounding the new structures in triangles in order to solve for missing information. And your essential question for the day: do I understand the new structures and their rules? You may have heard of some of these structures before, but I highly doubt it. I think this is going to be something that's going to be new to just about everybody. As always, press pause anytime you need more time in order to copy the notes down, and then hit play when you're ready to move forward. Okay, so let's get started. First new structure that we have is called an altitude. You have undoubtedly heard the word altitude before, and it means something quite similar in geometry as it does in the English language, although you may have to adjust slightly. An altitude of a triangle connects a side of the triangle to the vertex that is across from it, such that the intersection with the side is perpendicular. Again, an altitude of a triangle connects a side of the triangle to the vertex across from it, such that the intersection with the side is perpendicular. Now, typically when we think of the word altitude in the English language, chances are you think of height, distance up. Okay, that is typically what we think of when we think of altitude. But remember, our triangles can be turned any direction that they want to be turned. It must fit this definition. It connects a side to the vertex across from it, such that the intersection with the side is perpendicular. Okay, and one of the things you have to watch out for is altitudes do not necessarily have to be inside of a triangle. Okay, now if you have an acute triangle, like this guy, then anywhere that we position an altitude inside of the triangle, it will be inside of the triangle. Okay, so there is an example of an altitude. This line segment that just appeared, going from A to D, it is perpendicular to one side of the triangle, and it makes contact with the vertex that is across from it. However, if you're dealing with an obtuse triangle like this one, it may be impossible for an altitude to actually be inside of the triangle, but the definition must hold true. It needs to be perpendicular to a side and make contact with the vertex that is across from it. In order to do that, it may be necessary for you to artificially extend one side of the triangle in order to meet that requirement. Okay, so in both of these cases, the statement can be made that line segment AD is an altitude of triangle ABC. Now, in both of these instances, the altitude is going straight up, okay, straight up from a base or a side of the triangle, but that does not mean it has to go straight up. We very easily could have come from any side of these triangles as long as it was perpendicular to that side and made contact with the vertex that is across from it. Okay, another type of a structure, and you may have heard this term before, but again, it had a different meaning when you heard it, and that is a median. The median of a triangle also connects a side of the triangle to the vertex that is across from it, just like the altitudes did. However, a median does not care about right angles. What a median wants is it wants the side length to be bisected. Again, a median of a triangle connects a side of the triangle to the vertex that is across from it, such that the side is bisected. Okay. Hopefully remember from our vocabulary back in the day, bisected means cut exactly in half. So let's take a look at this in a diagram. Okay. Here is a triangle. A median connects a side of the triangle to the vertex across from it such that the side length is bisected. Okay. Now there is no reason that a median will ever get outside of a triangle, because in order to get to the midpoint of the side that it's connecting to, it should have to pass through the interior of the triangle. Okay. Medians can also go any direction. They can connect any side to any vertex as long as the definition is met. They must connect such that a side is bisected. And once again, in this case, the statement can be made that line segment AD is a median of triangle ABC. Okay, let's move on. Now, another type of a structure that we may see in a triangle is called an angle bisector. Now, this one probably makes sense just by reading the words. An angle bisector splits an angle exactly in half. Okay, splits an angle exactly in half. Okay, so here is a triangle. An angle bisector is going to be a line or a ray or a line segment. Okay, it's going to come from one of the angles, and it is going to, as its definition said, split the angle exactly in half. So we end up with two smaller congruent angles. We would be able to say in this case that ray BD bisects angle ABC. Okay. There's other vocabulary that can also apply here, because we've seen this word before, bisector, and there's a lot of different ways to communicate it. It could also say that angle ABC is bisected by ray BD, or it could be say that ray BD is a bisector of angle ABC. A lot of different vocabulary there, but it all has the same meaning. Okay, there's one more structure that we're going to look at before we switch gears slightly. If your bisector happens to be perpendicular to the object that it is bisecting, then it is called a perpendicular bisector. Okay, so that's a name that makes perfect sense. If a bisector happens to be perpendicular to the object it is bisecting, it is called a perpendicular bisector. Okay, so in a triangle, what we are looking for is a line segment that is perpendicular to an object that it is also bisecting. So you can see there where line segment ED is making contact with line segment AB. Not only is it a 90-degree angle that is formed there, but the line segment AB is cut exactly in half. So the statement could be made, line segment DE is a perpendicular bisector of line segment AB. Okay, now, if you were to apply each of these four terms that we just discussed to an isosceles triangle, here is what they would look like. Okay, so you're probably going to need to press pause on the video to get these guys copied down. Okay, but you have an altitude on the left side, and he has an altitude because he's perpendicular to a side of the triangle. You have a median on the left center. He is a median because he bisects a side of the triangle. You have an angle bisector on the middle right because he's bisecting the top angle there. And you have a perpendicular bisector on the far right because he's perpendicular to the object that he is bisecting. Press pause if you need a moment to copy those down. Okay, now there is a property that is existing right here. Okay, do you notice anything about the red line segments that we just put in all of those isosceles triangles? Now, all these triangles are drawn to scale. Everything is positioned and measured exactly as it should be according to its properties. And the thing that you would notice if you were to do the same, to take measurements and do all that of these triangles, you would notice that it is the exact same red line segment every single time. It is not even so much as a fraction off one way or another way, that it's the same line segment each and every time, regardless of the properties that these different terms carry with them. Altitude, median, angle bisector, perpendicular bisector, they all do their own thing, but the red line segment gets positioned exactly the same each and every time if the triangle is an isosceles triangle. So we have basically a property or a rule that's going to exist here. If you have an isosceles triangle, the altitude, the median, the angle bisector, the perpendicular bisector, they are all not only the same line segment, but when you discover one of these properties about your isosceles triangle, then you have all of these properties about your isosceles triangle. So for example, if you have a isosceles triangle and you know that you have a median, well, not only is that median going to be a median, it's also going to automatically be an altitude and have all the properties of an altitude, be an angle bisector and have all the properties of an angle bisector, and be a perpendicular bisector and have all the properties of a perpendicular bisector. So in an isosceles triangle, if you can find one of these segments, the properties of one of these segments, then you automatically apply all of the properties from all four of these segments. Okay? So let's take this one step further. Let's look at this isosceles triangle, okay, and the line segment that is in it. Now, you don't have to copy this guy down again, but I would like you to follow along with this page. Okay, so you may skip all of the notes that are on this page. Just please follow along. Don't tune it out and don't fast forward. Okay, let's look at the two smaller triangles that are inside of this larger isosceles triangle and consider the triangle shortcut postulates that we've already talked about. Now you should remember there's four of them: side, 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 angle, side, angle, and angle, angle, side. Okay, so let's see if we have enough information about these two little triangles, okay, to answer. Are we congruent with the two little triangles by the side, side, side congruence postulate? Well, let's take a look in the triangle. Now, as you can see, that triangle, I have basically installed all of the properties from all four of the different types of segments: median, altitude, angle bisector, perpendicular bisector. So they're all in there at once. Let's look for side, side, side. Okay, now if you look at the coloration that just showed up in the graph, we have the two red sides. They both have one tick mark. The blue side is the reflexive property, so it's the same in both triangles. And then we have the green side, which is congruent in both of the triangles by the two tick marks. So yes, we absolutely have enough information to prove those triangles are congruent by side, side, side. How about, are they congruent by side, angle, side? Okay, but once again, look at the coloration that I'm about to add to the problem. Okay, you have the two red sides. They are congruent by the tick mark. You've got the green angles in between the red and the blue side, so they are congruent. And then, of course, the blue side is congruent to both triangles by the reflexive property. So we have red, green, blue. Those are side, angle, side. Yes, you have enough information to say they are congruent by side, angle, side. How about angle, side, angle on these two little triangles? Okay, well, again, look at the coloration. You got the red angles there at the top. They are congruent. The green side is congruent to both triangles by the reflexive property. Then we got the little right angle guy down near vertex C. Okay, well, near vertex C, obviously, if you have a right angle on the left triangle, okay, it's also going to have to be a right angle on the right side in the right triangle. You can't have a right angle on one side of that line and not a right angle on the other. If it's perpendicular on one side, it's got to be perpendicular on the other. So yes, angle, side, angle does apply. How about congruence by angle, angle, side? Well, once again, the blue angles are still congruent up there. The green angles there at the right angle, they are still congruent. And the red guy down at the bottom, the 2 tick marks, that has them congruent as well. So blue, green, red, angle, angle, side. So enough information there. Okay, so we got all kinds of congruence. I wonder if we even have enough information to say that these 2 triangles are congruent without even using the shortcut. Let's look at the definition of congruence. Okay, in order to answer that, all corresponding angles from your 2 triangles have to be congruent. Do we have that information? Well, we know we have the blue guys up top. We know we have the right angles, the green ones there, near vertex C. And what about the guys out there at the angle near vertex B and the angle near vertex D? Okay, well, if you think about it for a second, we have 2 triangles. The interior angles from each of those 2 triangles are going to add to 180 degrees. So the blue guy and the green guy plus the red guys are going to have to add up to equal 180. Well, we know that the blue guys are the same. We know that the green guys are the same. And we know that all 3 are going to have to add up to be 180. The red guys are not going to have any choice except to be the same measurement. So all corresponding angles are congruent. How about all corresponding sides? Well, we already saw that with side, side, side. Your red guy, your green guy, your blue guy, they are definitely all congruent. So we have all corresponding angles congruent, all corresponding sides congruent. That means that, yes, they are congruent. So as you can see, this is a very important shape, okay, very popular shape in geometry, the isosceles triangle. There is a ton of information that they can ask you just by putting an isosceles triangle on a piece of paper. So you got to know all of those properties because we really don't know what kind of question they might choose to dive into with that isosceles triangle. Okay, back to the notes. One last segment. He is kind of different from the other ones. Okay, the rule here, if we were to connect the midpoints of 2 sides of a triangle, if we were to connect the midpoints of 2 sides of a triangle, let's take a look at that. Okay, we have a triangle. Okay, and we are supposed to connect the midpoints from 2 sides of this guy. So let's find the midpoints. One side, put a point, and we put it in the middle by making sure that it's equidistant on either side of that point. We got another side. We'll make sure it is the midpoint by making it equidistant from each corner. Okay, and then it says if you were to connect those 2 points. Okay, so there we have connected them. Okay, if you were to connect the midpoints of 2 sides of a triangle, this segment is called a midsegment. Okay, it's called a midsegment, and there is an additional property that goes along with being a midsegment. A midsegment is always parallel to one side of the triangle. Okay, it's very clear to see which triangle, which side it's going to be parallel to, but that is an important property. If you connect the midpoint of 2 sides of a triangle, then you have a midsegment which is definitely parallel to the 3rd side of the triangle. Okay. The last thing I want you to do is I want you to press pause here in a moment, and I want you to copy down this mess into your notes. This is a problem that we are going to work together in class, and I do not want you copying it down instead of listening to me talk to you about how to work it. So definitely get all this information copied down. In triangle JKL, line segment LJ is congruent to line segment KL. Line segment LM is an altitude. Line segment MN is a median. Find all of the missing variables. So please copy down all of that detail, then copy down this diagram, including all of the vertices and the information that is provided. We will cover this problem in class together. No need to try it on your own. Just please do get it copied down. Press pause now if you need more time. And the last thing that you will need to do is your summary. Jot down a little summary about what we have covered in this unit. Notate any questions that you may have, and keep your essential question in mind. Do I understand the new structures and their rules? I appreciate you finding time to get your notes taken care of. It's the last set of notes for the semester. Those of you that have been working hard on it, I really do appreciate it. You've been doing good. I'll see you in class.